Mic is not. Wait, is it right? Was it not right before? I can't remember. All right, didn't know. This thing is really flaky on me. I really need to get a new one. All right. So Rn is called the domain and Rm is called the codomain. The notation indicates that the domain of T is Rn and the codomain is Rm. Okay. For x, they're just setting up the notation. For x and Rn, the vector is called the image. Okay. Okay, this is a good picture. So the new terminology is important because a dynamic view of matrix vector multiplication is the key to understanding several ideas in linear algebra and building mathematical models of physical systems that evolve over time. Such dynamical systems will be whatever. Matrix transformations. The rest of this section focuses on mappings associated with matrix multiplication. For each x in Rn, T of x is computed as a times x, where A is an m by n matrix. For simplicity, we sometimes denote such a matrix transformation with that arrow. Observe that the domain okay, so I always like to think of columns as variable count and uh, rows as equation count. Okay, so observe that the domain of T is Rn when yeah. Okay, and the codomain is Rm when there's m entries, so m rows. The range of T is the set of all linear combinations of the columns of A. Yeah. Yeah. So we have T from Rn to Rm. Range T is all okay. The range of T is the set of all linear combinations. Okay, cool. So, all right, we have this example. We have a matrix that's M is 3 and N is 2. It is, I mean, the thing about linear algebra, I feel like, is that it takes a bunch of just, I don't know, for me, it just takes a bunch of doing the same stuff over and over again before it, like, starts to click. Maybe I'm just Okay, okay. All right. So we have these vectors and we have this matrix. And then we define the transformation, which is just the action of the matrix. Okay, and then we get, all right, I like that they show the equation form. It's actually messed me up on the quiz that we had to do recently. All right, wait, is it still? I'm really worried about this thing breaking. Because, like, I think I remember I took it apart on a stream, and the microphone, all the solder connections look good, but it does seem to just disconnect. All right. Okay, so the image of you. Okay, so we did that. I just did that just by myself. Find an X and R2 whose image is B. Okay, so we're looking for a linear combination of the columns that equals B. So we can do our normal augmented matrix thing and row reduce it, right? So 1 minus 3, 3, 3, 5, 2, minus 1, 7, minus 5. Oh. Okay, so we're not going to manually row reduce. Well, maybe I will. Okay, so I did it. So now you have 1, 0, 3 halves, 0, 1, minus 1 half. And we're trying to find where B is equal to 3, 2, minus 5. Okay, I got it. Yeah, it's kind of weird that when you have an augmented matrix and you row reduce it. Okay, so we did um is there more than one x whose image under T is B? I don't actually know that. How do I do that? I don't think there's any free variables, so I'm guessing no. Okay, so this is what I got. It has a unique solution. Why is it that clear? Okay, and then what is D? All right, so that's C is the exact same problem as B. Wait, I scrolled too far. Yeah, it's consistent, right? Okay, and it's not. Okay, so the question uniqueness problem. Oh yeah, that's the difference. Oh, did it say unique? Or I guess that's okay. Nice. Does there exist an X whose image is C? The next two matrix transformations can be viewed geometrically. They reinforce the dynamic view of a matrix as something that transforms vectors into other vectors. Okay, so that's a projection. Okay. All right. Such a beautiful morning. Oh, springtime. All right. Okay, so this one's pretty clear to me. Yeah, it just puts it onto a plane. Okay. The third example is, let's see, let's make it an equation. So it's going to be x1 plus 2x2 and x2. If we row reduce it, let's say we have on the augmented, we have an a and a b. Then we're going to do r1 is equal to r1 minus 2r2. And so we're going to get a minus 2b for x1. x2 is going to still be equal to b. So think about what that transformation does. What is it that transformation does? If let's just say that we apply 1, 1 to it. So we have a vector geometrically just 1, 1. It's going to, I know it's going to shear, but I want to just apply it myself. So we're going to get 1, 1, 0, 1 times 1, 1. And we're going to get 2, 1. So yeah, it's going to stretch outward. But now if we gave it like 0, 1, oh no, it does still shift it. Okay. So even 0, 1, the vector that points up, so that this edge, it all gets sheared. Okay. So yeah. It's called a shear transformation. It can be shown that if t acts on each point in the 2 by 2 square, shown in figure 4. So it's it's the other angle. So if we gave it 1, 1, 0, 1 times 1, 0, this is going to stay at 1, 0. So this vector doesn't change, but everything else does. It can be shown that if t acts on each point in the 2 by 2 square shown in figure 4, then the set of images formed. The set of images forms the sheared parallelogram. Oh, okay. The key idea is to show that t maps line segments onto line segments. And check that the corners of the square map onto the vertices of the parallel. Oh, okay. Sure. For instance, the image of the point 0, 2 becomes 4, 2. Oh, I didn't shear. I sheared it. Okay, that's fine. And 2, 2, which is the top right corner. Shear transformations appear in physics, geology, and crystallography. Interesting. All right, so now we get to some of the definitions. All right, linear transformations. So matrix multiplication distributes over addition of vectors. So for A, B, and R, N, and A, big A in R, N by RM, or no, M by N, then A plus B is equal to AA plus AB. So that's the first one. Second one is that a scalar can be pulled out of it. Okay. Okay. These properties define what it means for a map to be linear. It's kind of a fundamental thing, huh? So I wonder what the transformations look like if you like got rid of one of the two. Like what happens if you throw away this property that you can't pull out the scalars? You know? I mean, clearly it's a not linear transformation, but like if you keep this one, but then you throw away the other one, just don't. What does that look like? Okay, so I just verified it for a basic function. I verified that f of x equal to 2x is linear. Every matrix transformation is a linear transformation. Important examples of linear transformations that are not matrix transformations will be discussed later. Linear transformations preserve the operations of vector addition and scalar multiplication. Property I is the result. Okay. All right, so this leads to, okay, so these are consequences of that then. T of 0 is equal to 0. Yeah, this one's obvious. You do the distribution and then you pull it out. Okay. Property 3 follows from condition 2 because, oh, okay. Sure. Yeah, 0 U. And property 4 requires both of them. That makes sense. All right. If a transformation set, so I don't know if I proved it or I just tested on an example. That's what I think really happened. We can see the results graphically. I don't know exactly what you were talking about, but yes. I actually really enjoy I enjoy the geometric interpretation of linear algebra a lot. And you know what I wish they would do? I mean, I understand why they don't, but I have this book, Ideals, Varieties, and Algorithms PDF. This book, excuse me, it describes this stuff called algebraic variety. And what to me, algebraic varieties are basically a generalization of, I mean, I don't know, maybe it's lame to say this, but like um in the polynomial case, right? Because for linear algebra, you could think of it as a variety. Let me see if I get this right. You could think of like let's just say the set of n by n matrices. You could think of it as a set of as a variety with I don't know. I don't actually know what the let's see what the definition is. How do they? Because I remember there's this notation. So it's a set of I'm pretty sure polynomials over a field that go to 0. So what I'm saying is that you have uh actually can we do this? I don't have but I'm pretty sure it's just you have a bounded degree on the polynomial, and that's pretty much it. So it's just like a small subset of what the full case is. But it's an interesting case, and and the all that nonlinearity and stuff, it makes it probably way harder to whatever. All right. Uh, okay. So what's cool about 4 is that if for all UV CD, so these are Rn, these are R, that T CU plus dV is equal to CTU plus DTV. Then T is linear. So that's nice because then you only have to remember one rule as opposed to two, even though it's the combination of two rules. Um, right, and you can just yeah. So that's cool. Okay, so that's kind of nice. If whenever an input is expressed as a linear combination of such signals, the system's response is the same linear combination of the responses to the individual signal. Oh, right. Yeah. Yeah, yeah, yeah. Okay. Okay, this is a cool problem. Yeah. All right. So show. Okay. So t from R2 to R2 be defined as Rx, R in as a real. Show t linear. All right, so we have t cu plus dv. So what we can do here is equal to ctu plus dtv, and we know. So when we said let r equal 3, so we'll rewrite this. So this is going to be CRU plus DRV is equal to C times 3U plus D times 3V. So wait, I don't think I did it in the steps that they did. So instead, if we just did 3 times CU plus DV. Okay, so yeah, if you can get it into that form. Okay. Just write that down. So we get 3CU plus 3DV. Then we get C3U plus D3V, which is equal to CTU plus DTV. Therefore, satisfies equation 4. Okay. All right, we'll just use my webcam mic. This thing, I gotta get a new one. Every time I touch it, it's just so fucked up. I mean, I tried fixing it, but if I can't fix it, should I just buy a new one? Should I support the fact that they built something? I mean, I did abuse the hell out of it. So maybe, I don't know. But it sucks. It's like it should be fixable. Let me see if I can get it. I tried fixing it, so I did really put in the effort. Oh wait, is it working now? Or is this the wrong mic? No, I think it's working now. Okay, so I just have to not touch it for today, and then buy a new one, I think. Okay. Wait, is it working? All right. I'm just not gonna touch it. All right. Okay, cool. Okay, this is just basic math, taking matrix vector multiplications. The final example is not geometrical, and instead it shows how linear mapping can transform one type of data into another. A company manufactures two products, B and C, using data from example 7 in section 1.3. Using data, we can construct a unit cost matrix. Okay. Cost per dollar of output. Okay. Yeah. So, yeah, that makes sense. You have this. Okay, that's pretty easy. The mapping T transforms a list of production quantities measured in dollars into a list of total costs. The linearity of this mapping is reflected in two ways. If the production is increased by a factor of 4 from x to 4x, the costs will increase by the same factor. Okay. If x and y are production vectors, then the total cost vector associated with the combined x plus y is precisely. Hold on. Right. Yeah, yeah. Okay. All right. Practice problems. Ugh. All right. Practice problems. Let's do it. T goes from R5 to R2. Let's do a simpler one. T goes from R2 to R1. So it's gonna have 2 rows and 5 columns. Similarly, for the small case, it's gonna have 2 by. So if we go 2. Wait. Is that right? No. It's 1 by 2 and it's 5 by 2. It's gonna have 5 rows. Okay. So wait. Why is this problem tripping me out so much? What the hell? Yeah. Okay. So it's going to have 2 rows and 5 columns. And the way to think about that is columns is the same as the number of variables in the equation form of the linear transformation. And so it's going to have 5 inputs for one for each of the, in the linear combination of the columns. Okay, yeah. So that checks out. So it's going to have 2 rows and 5 columns. All right. Give a geometric description of so let's just say what it does to 1, 0 is equal to 1, 0. Then to 0, 1, it becomes 0 minus 1. So geometrically, let's figure that out. So this stays here. And then we have this point, and this point goes over to there. So what about 1, 1? 1, 1 goes to 1 minus 1. Or wait. No, this is 0, 1. This gets flipped down to here. Okay, so I think, yeah, so geometrically, it is a reflection around the x-axis. I'm pretty sure that's true. Okay, number 3. The line segment 0 to a vector u is the set of points that form of the form tu. Right. Show that a linear transformation maps this segment into this segment. Show that a linear transformation T maps this segment into this segment between. Okay. So let's just draw a little picture. So you have 0 and then u. Now we're trying to say. Show that a linear show. Okay, so if we take little t is equal to 1, so we know that t is a linear transformation. We can assume that. So then we can use those properties that they spelled out. I feel like I'm gonna have to keep checking the how to solve complex problem like you have. What? Right, you just gotta do it. All right. Okay, so if little t is 1, then we're gonna have, I guess, evaluate the corners. So we're gonna have t0, and that's 0. So I guess we showed that. Now we have, or actually, we just applied t to little tu, and we know by linearity that this is little t big Tu. I mean, I think it's literally just an application of this. I don't even really think that you need anything besides that property. Okay. We'll see let's actually go down and see what they say. Let x equal tu for some t between 0 and 1. Okay, great. That's exactly what I did. You just pull out the scalar and you show that that's that. I bet there are probably some fun applied problems in this section. Actually, it doesn't really look like it. All right, so now let's read through the problems and just see what kind of stuff is in there and which ones we want to do. Okay, where are we at? Okay, we are at reading the exercises. Okay, so we have this matrix. Find the images. Okay, that one's easy. It's going to be 2A, 2B, right? So this one will then be 2 minus 6. Okay, this is a contraction. It's just going to be 1/2, 1/2, 1/2. So 1/2, 0, minus 2. Okay, so we did those. All right, basically, again, this is just reinforcing the idea that there's another way to think about these linear systems, these augmented systems or whatever, and it's through matrix vector multiplication. So AX is equal to B. Okay. So, I mean, basically a bunch of RFs. We can do a couple of those. A is a 4 by 6 matrix. What must A and B be in order to define okay. So 7 is we have a 4 by 6 and we want T R A to R B. A is 6, B is 4. Let's do it with the simpler one, 2 and 3. So we get A, B, C, D, E, F times X, Y, Z. Yeah, I'm pretty sure that's true. All right, how many rows and columns must a matrix have to find a mapping from R3? Okay, so then 8. We have T that goes from R3 to R6. So then it's going to be a 6 by 3 matrix. I guess another way to think about it is that the number of the input dimension and the number of variables, i.e., the number of columns, has got to be the same. Otherwise, you can't even evaluate it. All right. All right. Exercise 9 and 10. Find all x in R4 that are mapped into the 0 vector. Okay. So this amounts to reducing it and then putting it in, what is it called, parametric vector form or something like that. Oh, it's the general solution. Oh yeah, no, parametric vector form. For non-homogeneous, where's the homogeneous case? It's good to review this stuff. Okay, so yeah, so this is what we get. To verify, oh, this is just verification, but you found homogeneous solutions to be this. Okay, so this is that parametric vector form. So that was what I was thinking. Okay. So yeah, so you basically reduce it and write it in parametric vector form. We'll do one of these. That's fine. Let's just do it right now. Why not? I don't even know what that is. For gate? I don't even know what that means. All right. So you got this. Now you got this. Now we'll just call R ref of A. Gotta wait for it to start up. All right. Let's keep reading. Wait, what? Oh, wait. Okay. Yeah. So 11 is the same as these 3 through 6, I think. Basically, is the system AX equal to B consistent? Okay. This is the same one as 11. Plot the image of a bunch of vectors. Okay, that's all good with me. Describe geometrically what it does. Okay, so this is going to be a reflection across 0. You know, so basically a reflection across the x-axis and the y-axis. This is going to be a contraction, dividing all vectors by 2, making them smaller. This is a projection. 15 is a projection where let's say you have a vector on the plane, the xy plane, and it's like 1, 1. 1, 1 is going to get mapped to 0, 1. So it's going to be a projection onto the y-axis. This one is interesting. This one is going to, I think this is going to be a rotation, or not a rotation, but a reflection across the x equals y line. That's what I think that one's going to be. But we'll check that one. I study 26 hours a day. Get fucked. No, I don't know. All right. So here, so wait. This is interesting. Okay, I actually want to write this one out because this is pretty interesting. So we have x1 is equal to 9x3 minus 7x4. x2 is equal to 4x3 minus 3x4. And then x3 and x4 are free. So that's what that means, because these two columns don't have pivots, right? So then we don't have any way to reduce those any further. So what that means is that to write this in parametric vector form, we're going to get x1 times 9x3 minus 7x. Actually, reviewing this is probably good because I haven't done this in a second. This is going to be... Wait, if I just... All right, I think I'm gonna review the textbook for a second because I am forgetting this parametric vector form stuff. Okay, this is exactly what I was looking for. So ours is homogeneous, so we just have an extra zero column that they don't have. But yeah, so the solution x is equal to 9x3 minus 7x4, 4x3 minus 3x4, and then x3, x4. So that's the solution. So then we basically factor it all out, right? Okay, so I think that so if we go back to this problem, 9, find all x that are mapped to the 0 vector. So I'm pretty sure that that solution is going to be no, I don't know. I don't keep track. All right, so I'm pretty sure that the general or the parametric vector solution of this is we're gonna have, let's just do variables x1, x2, x3, x4. So we should have x 3 times the vector 9, 4, 1, 0 plus x4 times the vector -7, -3, 0, and 1. So this should be this is parametric vector form of the solutions to ax equals 0. Okay, so that's that. That's pretty good. All right, where were we? So we did all of these, but I wanted to verify this one. So if we give it 1, 1, or if we give it 0, if we give it 1, 0, let's just do that. So I'm number 16 right now. Make sure my mic is still working. All right, 16. 0, 1, 1, 0 times 1, 0 is equal to 0, 1. Similarly for 0, 1, 1, 0, 0, 1. Okay, so now, okay, but if we apply, let's say 1, 1 to it, 0, 1 times 1 of 1, 1, we're going to get 1, 1. So I'm pretty sure, yeah, that the way to think about this transformation is that it's a flip over the y, or the y equals x line. Maybe we could test it with another example of if we send it to, if we give it 2, 1, we give it 2, 1. We're going to get 1, 2. Yeah, it just flips it across. So that's good. All right. 17. R2 to R2, the linear transformation that maps 17 AX So for in the ax equals b thing, we're going to have a times 2, 1 is equal to 3, 4, as well as a times 1, 2 is equal to 1 minus 5. I like these problems because it's like, use the fact that t is linear. Okay, so if we have a times 5 u, so this is u and this is v, is equal to 5 times AU. So we don't actually need to know what A is. So I was thinking of like, how do you reverse engineer what A is? But you don't actually need to do that because you can recognize that it's just going to be, if you pull the scalar out by the definition of the linear transformation, you get 5AU, which is going to be equal to 5 times 3, 4, which is going to be equal to 1520, or 1520. Okay. Similarly, for the next one, we're trying to find 4v. So we're going to get just 4 minus 20. And now 5u plus 4v is going to be equal to 19, 0, I think. All right. 18. The figure shows vectors u, v, and w along with the images and the action of the linear transformation from R2 to R2. Oh, that's weird. I don't know how to do that. So the 0, 1 vector is what we're trying to find what it goes to. But the 1, 0 vector, '18 is a good problem. I like 18. Right, W is a linear combination of U and V. That's actually a good idea. Oh, yeah. Okay, so it's going to be like W. So for 18, it's going to be like W is equal to U minus 3V or something like that. Okay. A little bit. But I haven't taken a complex analysis class, so I don't like, you know. Okay, I got to think about that one. Okay. All right. Whoa. Okay. So, Yep. Use linearity to build T of X once you know T, U, and TV. Okay, so now we have, okay, so wait, hold on. So T of X is going to be equal to, yeah, T of A U plus BV is equal to ATU plus BTV. It's just going to be equal to, right, and that's a linear combination itself. So then you're going to get TU, TV, AB is what is equal to T of X. So then we plug in so then A Okay. All right. So this has been a fun detour problem. It's to figure out actually what is the matrix. So T of X is equal to TU TB and UV inverse times X. So we can get rid of the X and just say that T is everything but X. That's pretty cool. Let's see what it actually is. Or did he already do that with this? All right, so I guess it was that. All right, nice, very good. All right, let's see what else is in this thing. Okay, so let's just say we have a matrix A, B, C, D. It's 2 by 2. And then we have a 1, 0. So what we know is that wait, what? We know that TE1 is equal to 2, 5. Okay, so what we know is that 1 times AC plus 0 times BD is equal to 2, 5. So then we already know that A is equal to 2, C is equal to 5. I mean, it has to be, right? So we already have the first part of the matrix, so it's going to be 2, 5, and then BD. And for that, we're going to have ABCD times 0, 1 equals what? Minus 1, 6. So that was a minus 1, 6. So we're going to get B equals minus 1, D equals 6. So the full matrix of T is equal to 2 minus 1, 5, 6. Okay. So let's just do the general one. I don't really want to do a calculation right now. So this times x, y, we're going to have 2x minus y and 5x plus 6y. Okay. I'm going to confirm. I already did the answer, but I'm going to confirm it. Let's see. All right. Cool. That was easy. All right, let's do the true falses, and then maybe we'll just move on. Oh, actually, 24 I think might be false. I don't think because the codomain can be bigger than the range. I'm pretty sure that the set of linear combinations of the columns of A is not the codomain but the range. Okay. If the range, I think that's also false. We don't really know anything about the dimension of the range. Okay, 26. This would be true if you 25 would be true if you replaced range with codomain. The codomain of this transformation is R. Okay. 26, if R and Rm is a linear transformation in C, then a uniqueness question. I 26 I think would be false because if the codomain is trying to think, but I'm pretty sure that you could have multiple solutions. So the fact just answering whether or not C is in the range doesn't answer if it's unique. Every linear transformation is a matrix transformation. That's false. I don't know what else there is, honestly, but linear transformation preserves the operation of. Yeah, that's true. A transformation is linear if and only if. Yes, that is true. That's just the definition. What? The superposition principle is a physical? What did they even say? I didn't even get that part of it. Okay, I guess that's true. It's a physics thing. Okay, wait, we already did it. All right, so wait, I'm just gonna copy these and see what. It's so annoying that you can't. Oh, there we go. You can. All right. Ah, okay. I'm just gonna check our answers. Let's see what else is in this thing. Actually, it's these problems after in this textbook. The problems after the true false are the best ones. Like I want to do this one. Let's do these two for sure. Those are cool. Okay, true, true, false, false, 25, false. Yeah, only row rank, full row rank. Yep. 26, false. 27. Was that true? 27, I wrote false. Uh, every linear transformation. I think that might not be that important. But hold on, let's where does it say in chapter whatever we're gonna. Here we go. Every matrix transformation is a linear transformation. Examples of linear transformations that are not matrix. Okay, so I'm right in the context of this book. I think. Okay, and then 28 true, 29 true, 30 true. Okay, so we got all but that one right. And that one I think is more of a, I don't know, technicality or anything. Oh. I think they want us to answer false, but anyways. I wanted to do, let's read some of these more ones, then we're going to switch over to Diffie. I'm going to read 1.4 and then we're going to do some stuff. Okay. Okay, 32 seems cool actually. So we'll say span V1 VP is equal to Rn. T is of Rn to Rn. And for I that's a good problem. I got to think about that one. Okay, I think so I think for the first thing that was obvious to me is that P is greater than or equal to N. I think that that's true. Okay, so just a reminder, this is the problem I'm working on. I don't know how to show this one, man. I'm stuck. Because, like, okay, if every one of our vectors gets sent to the zero vector, then let me think. If every one of our vectors gets sent to the zero vector, what we know is that out of the set of vectors v1 to vp, there have to be at least n linearly independent vectors in that set. Okay, so let's I mean, I guess what I'm trying to say geometrically is like the thing that has to be doing. Okay, all right. I'm gonna get the answer now. I just want to know how to approach it. Yes, that is true. Okay, so you distribute. Wait. Right. Oh, okay. You know what? That's actually that's actually a good proof. Yeah. So the proof of this is um, because V1 to P spans Rn, then for all x, we can write x as x equal to the sum of Ci Vi from 1 to P. 1 to P. Okay, so this is just a linear combination. Okay. Um, so then we take T of x. T of x is going to be equal to um, T of the sum from Ci Vi, which is equal to the sum of T Ci Vi, which is equal to sum of Ci times T Vi, and this is 0 for all Vi. So therefore, we're going to get the sum of Ci times 0 is equal to 0. So so x can only, or Tx can only be 0. Yeah, there's no way to like try to squeeze out some space from somewhere else because basically there's no getting around the linearity. That's a very good problem. That's my favorite problem from this so far. A really good one. Okay, so given v is not the zero vector and p is in Rn, the line through p in the direction of v has the parametric equation x is equal to p plus tv. Show that a linear transformation from Rn to Rn maps this line onto another line or a single point. All right, this does seem like a pretty good problem too, actually. See, these are the problems that I feel like we should be doing because they're 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 harder. You know, it's not just computing; it's like actually thinking about what's going on. right. All right, I think I'm going to draw some pictures. Just try to get a sense of what's going on. So let's let v equal to 1, 1, and p equal to 0, 1. So then we're going to have this line that goes through 0, 1, has a slope of 1. Okay? Now we're trying to show that t r2 to r2 is maps this line to other line or a point. So that's pretty interesting. That's pretty interesting. So, I mean, the obvious thing to do is we have x is equal to p plus tv. T is in r. So now we're going to just take t of x, big T of x, which is going to be equal to t of p plus tv. And then we can just apply linearity. So we get tp plus little t tv. I mean, so this is what, so let's say t is equal to tx equals 0 for all x. In that case, we're just going to get a point. We're going to get the 0 point. So t of x equals 0. So that's the obvious case. So we've shown that we can just get a point by making that linear transformation the 0 map. Now, if it's the identity map, if t is equal to I, then we get the same line. Now, let's say that t is our let's say t is that map that does the flip across the x equals y axis. In that case, we're gonna get t of x is equal to t of 0, 1 plus little t t of 1, 1. So 0, 1, 1, 0 of 0, 1 is equal to 0, no, is equal to 1, 0. And then 0, 1, 1, 0 is equal to times 1, 1, 2. So we're going to get 1, 0 plus t times 1, 1. Okay, so it did mirror it across. So now that I've done something, I'm going to look at the answer. Because I don't really know what's going on. Yep, so I did that. The image of L, yeah, is that. That's right. If t is not equal to 0, or if t of v is not 0, okay, if it is 0, So I guess one thing that I didn't mention is it's possible for t of v equal to 0, but not t of p. Is that true? Okay, that one's a good problem. All right, 34. All right, let me read it. Let u and v be linearly independent vectors in R3. Let p be the plane through u, v, and 0. Okay, the parametric equation of p is su plus tv. Show that a linear transformation maps p onto a plane through 0, or onto a line through 0, or onto just the origin. What must be true about tu and tv in order for the image of p to be a plane? I mean, clearly it's that that tu and tv need to be linearly independent. That's obvious. So, I mean, without ruining anything, we could just take u equal to 1, 0, 0 and v equal to 0, 1, 0 because that's linearly independent and they're, simple to deal with. So now, in this case, this is the plane in R3 for xy plane. This is just the xy plane. So the parametric equation is going to be x equal to s times 1, 0, 0 plus t 0, 1, 0. So that's pretty obvious to see how we can get any point in the xy plane. But now we want to show t from 3 to 3 is either map p to plane a plane through 0. I like these ones that have no affine funny business. I don't really like, I don't know. I guess I do like affine stuff, but it's just harder to conceptualize it, I think. Okay, so okay, I have an idea. Okay, so I basically think I figured it out. I mean, okay, so for all S, T, and R. So basically, I mean, it's the same as the last problem, where it's like first we apply linearity to get STU plus TTV. And basically, there's a couple of cases. So either TU independent of TV, plain case, and it must go through zero because of S T equal to zero. If you set S and T equal to zero, then it has to have the point zero in the map. So that's all good. Or not in depth and get a line. If TU equal to TV equal to zero, then just all right. So I want to see how GPT answers it, but I'm pretty sure it's exactly how I answered it. Okay, so I did this, apply linearity. Right, yes. So yeah, so the way to write that is T of P, where P is equal to the set of X. Right, so this is P. Is equal to the span of TU and TV. Yes. The zero subspace, but they're dependent or they're plane and they're linear. Okay, cool. So that's exactly what I thought. Show that the line through the vectors P and Q in Rn may be written in the parametric form. Show that a linear transformation T maps this line segment onto a line segment or onto a single point. Let's say that, yeah. Let's say that for the sake of this, that Q is equal to like -1, 0, and P is equal to 1, 0. So they both lie on the x-axis. And then the transformation T is, from R2 to R2, but it's a projection onto the y plane, then it's going to map onto a single point. So I don't know if I want to write all that one out. Okay, so I already did this earlier, actually. Find a property that, okay, I didn't do B though. Let's see, 37B. So f of x is equal to mx plus b. We want to say, so we're trying to compute f of ax plus by. And that by linearity, we should, so let's just take a equal to 2, x equal, or a equal to 1, x equal to 2, b equal to 3, y equal to 4. I'm sure that that will cause problems. So let's make a 5. So we're going to get f of 5 times 2 plus 3 times 4. So what we should get is f of 10 plus 12 is equal to f of 22. Let's say m is equal to minus 2 and b is equal to 4. So then we should get minus 2 times 22 plus 4 is equal to minus 44 plus 4 is equal to minus 40. Now if we apply linearity, we should get 5 times f of 2 plus 3 times f of 4. So f of 2 is equal to 0, because we're going to get minus 2 times 2 plus 4. Okay, f of 4, however, is equal to minus 8 plus 4 equal to minus 4. So we're going to get 5 times 0 plus 3 times minus 4 is equal to minus 12. And these two are not equal. Minus 12 is not equal to minus 40, contrary to what you might think. But we actually need to find the property that's violated. And I kind of want to think about this geometrically, really. So if we simplify, because that's the fully general case. So we showed that it doesn't hold, but we didn't say why. So if I do f times ax equal to a f of x, let's see if the scalar multiplication holds. So ax is equal to 10. So f of 10 is equal to minus 20 plus 4 is equal to minus 16. Now here, f of 5, or 5 times f of 2 is going to be equal to 0. So scalar multiplication breaks. All right. Why is f called a linear function? It's a parametric, or it's an affine line. I'll just say affine, because it forms a line. Okay, so when b goes 0, I didn't actually verify that, but because I did that earlier. Okay, so it. Oh, actually, that's the better way to do it. It's just test where 0 goes. Yeah, right. Easier is f of 0 equals 0, but if b not equal to 0, then this fails. That's a good way to do it. An elementary algebra is said to be linear because it makes a straight line. But it's actually, yeah, it's such a big lie. In school, they tell you that's linear, but it's not really. Thanks, Vesey. Okay, an affine transformation has the form. Show it's not a linear transformation. Well, we can just see with the same thing, the 0. And I think above, yeah, we had a corollary. Yeah, there's so many problems. Okay. Okay, so I mean the key to 40, you don't need to do very much other than recognize that the nonlinear function is clearly this, and you just say let f of x equal to absolute value of x. Then you can say try to apply linearity for distributivity, and you say x equals -1, y equals 1. The sum of those is 0, so abs of the actual sum is 0. But then abs of -1 plus abs of 1 is equal to 2. So you can show that linearity is violated. This one, oh, the affine, you just send it to the 0 vector and show that that t of x, t of 0 is not 0. So that one's easy. All right. I'm getting ready to end this section and move on to differential equations. Okay. All right. 42. Let T Rn to Rm be a linear transformation. Show I might take a break right now because I think that it's going to get really noisy and I don't really want to deal with that. I'm going to walk. Show that if T maps two linearly independent vectors on the linearly dependent set. That's actually a pretty good one. Okay, but I think we're going to call it here. That is the introduction to linear transformations. You guys can't hear it because of the noise reduction, but it's actually so loud. All right, I'll be back in like 30 minutes probably.